What if I told you that you have never actually touched anything? Not your chair, not your phone, not even another person's hand. That sounds like a cheap paradox. It isn't. It's the sober way physics describes contact. Every time you think two objects meet, what really stops them is a cushion made of electric fields and quantum rules. Tonight, we'll prove it. Show why touch is an illusion that keeps the world from collapsing, and explain the everyday consequences, from friction and heat to touchscreens, geckos, and even neutron stars. Start with something familiar. You sit on a chair. Your weight pulls you down with gravity, mg. The chair pushes up with the normal force, N. In school we draw N as a simple arrow. But where does that arrow come from? There is no tiny jack hidden in the chair. The push is electromagnetic. The atoms in your clothes and skin carry negative electron clouds surrounding positive nuclei. As those clouds approach the electron clouds in the chair, two things happen at once. Like charges repel, Coulomb's law, and quantum mechanics refuses to let identical electrons crowd into the same quantum states. The Pauli exclusion principle. The result feels like an invisible spring. Try to compress the two sets of atoms into the same space, and the energy cost shoots up. That rising energy with shrinking distance is the do not pass that you call touch. Important detail. The Pauli effect isn't a force you can point to like gravity or magnetism. It's a rule about the allowed states of matter. But when you try to overlap electron clouds beyond what their quantum states allow, the system's energy increases and pushes the atoms apart. In practice, that push shows up as a pressure, what engineers and physicists happily treat as a repulsive contact force. So the normal force N is really the sum of countless electromagnetic repulsions plus quantum state crowding resisting further overlap. Zoom in. An atom is mostly empty space. The nucleus is 10,000 times smaller than the atom's overall size. The surface of matter is not a hard shell. It's a fuzzy border where the probability of finding electrons drops off. When two solids come into contact, their electron clouds start to overlap at distances on the order of a fraction of a nanometer. That's still millions of times larger than nuclear size, and it's where your everyday world happens. Repel here, stick there, slide sometimes, grind sometimes. Nowhere in normal life do nuclei ever touch. If they did, you'd be doing nuclear physics with your fingertips. If contact is electromagnetic repulsion, why does it feel so unmistakably physical? Because your skin is full of mechanoreceptors, little biological sensors tuned to stretch, pressure, slip, and vibration. When a surface pushes on your skin, it deforms the outer layers by nanometers to micrometers. Ion channels in those nerve endings open. That is touch. Your nervous system reporting how strongly external electric fields prevented further overlap of atoms and how your skin deformed under that push. In other words, you feel a field, not matter. Your phone agrees. Most modern screens are capacitive touchscreens. They set up an electric field across a transparent grid. Bring a finger close and your conductive, salty skin changes the local field. No sparks, no microscopic hooks, just a tiny change in capacitance. The electronics notice and say, "Ah, a touch." You didn't have to scrape atoms together. Adjusting a field was enough. Okay, you might say, but I rub my hands and they get hot. Surely that's real contact. Rubbing is where the illusion of smooth surfaces breaks. On any flat surface, magnify enough and you see asperities, tiny mountains and valleys. As you slide, those high spots, where the electron clouds overlap the most, lock and unlock, stick and slip. Chemical bonds flicker on and off, atoms tug, then break free. The jolt energy turns into vibrations of the lattice, phonons. You call that heat. Again, no hard billiard ball contact, just electromagnetic forces rearranging and generating thermal motion as a receipt. Friction comes in two flavors that your skin can feel. Static friction, the force that resists the start of motion, and kinetic friction, the usually smaller force once things are sliding. Why is static friction larger? Because at rest, more of those tiny junctions, micro-welds, can settle into short-lived bonds. To start moving, you have to break a bunch of them at once. Once sliding, fewer bonds live long enough to form before breaking, so the average resisting force often drops. If you add soap or oil, you insert a new medium, molecules that prefer to stick to the surfaces and to each other in a way that keeps the big solids farther apart. Hydrodynamic lubrication builds a flowing film that carries the load, and the solids touch even less. Slippery is just more distance, less chance for those atomic stick-slip events. What about sticking on purpose? Like a gecko walking up glass. Gecko toes are covered in millions of tiny hairs, setae, ending in spatula-shaped tips. Those tips get so close to walls that the fluctuating electric fields between molecules, the van der Waals forces, add up. Each interaction is weak, but the total over such huge contact area is strong enough to hold the gecko's weight. When the gecko peels its foot, it changes the angle and spacing, turning off enough of those little attractions to release. Again, fields and distances, not hooks and glue. Let's press the concept until it bends. If nothing really touches, why don't we fall through the Earth? Because those same rules, electron repulsion and Pauli exclusion, scale up into bulk properties like stiffness and pressure. Try to squeeze ordinary matter too tightly, and its electrons resist. Try to pack them into fewer states, and the exclusion principle fights you harder. Remove that quantum rule in a thought experiment, and solids would flow into themselves. Reality keeps the rule. When you push on a table, you push on a quantum pressure wall. It feels solid because at human scales it is. You meet a dramatic version of this in compact stars. In white dwarfs, gravity tries to crush matter into a smaller volume. Electrons resist by Pauli exclusion. You can cram only 2 electrons per quantum state, so squeezing forces them into higher momentum states, creating degeneracy pressure. That pressure holds white dwarfs up against gravity without any thermal heat source. In neutron stars, gravity pushes past the point where electrons and protons can remain separate. They combine into neutrons. Then neutron degeneracy plays the same role. You could say a neutron star is what matter looks like when the no-touch rule is enforced by neutrons instead of electrons. Either way, the lesson is the same. The solidity you rely on is a quantum refusal to share states. Back to Earth. Let's clear a common myth. Electromagnetic repulsion alone keeps atoms apart. Half true. As 2 neutral atoms approach, their electron clouds first attract slightly, induced dipoles, London dispersion. Then, at very short range, the antisymmetry of electron wave functions, Pauli, dominates and produces a steep, effective repulsion. Realistic atomic potentials, like the Leonard-Jones curve, have a shallow well where molecules bind, and a sharp wall, where do not enter lives. Chemical bonds form at the bottom of that well. Hardness lives on the wall. So both attraction and repulsion are in play, depending on distance. What about touching electrically charged things? Bring two identical charges together, and Coulomb repulsion keeps them apart at longer range than neutral atoms. Bring opposite charges together, and they pull closer, lower the energy, and form a bond. But even in ionic or covalent bonds, nuclei do not meet. Electrons spread out into shared orbitals, and equilibrium distances settle around fractions of a nanometer. Bonded atoms are closer than contacting solids, but they're still separated by wave functions that refuse to collapse into a point. You can actually feel this distance if you go small enough. The scanning tunneling microscope, STM, images surfaces with a needle that never touches. It places a sharp metallic tip a few angstroms above a surface and applies a voltage. Even though there's a gap, electrons can quantum tunnel across it. The tunneling current decays exponentially with distance. Move the tip 1/10 of a nanometer closer and the current can double. By keeping the current constant and scanning, you map the surface atom by atom, without contact. Non-contact atomic force microscopes feel van der Waals forces and other interactions with a vibrating cantilever. In both cases, the handshake is forces and tunneling across a gap, not compression of hard shells. Speaking of tunneling, doesn't tunneling mean particles sometimes pass through solid barriers? Yes, with tiny probabilities when the barrier is thin and the particle energy is near the top of the barrier. Alpha particles tunnel out of nuclei in radioactive decay. Electrons tunnel through thin oxides in flash memory. But even tunneling doesn't involve billiard ball contact. It is a wave function leaking into and through a region where classical motion would forbid it. Your hand doesn't tunnel through a table because the numbers are absurd. The chance is effectively zero over the distances and masses involved. Here's a playful test of the field, not matter idea you can do at home. Rub a balloon on your hair to charge it and bring it near small scraps of paper. The paper jumps before the balloon touches. The balloon's electric field polarizes the paper, pulling negative charges slightly closer, positive slightly farther, and the closer side experiences a stronger attraction. That's touch without touching in miniature. Magnets do a similar party trick with ferromagnets. Field first, motion later. But then, why does punching a wall hurt? Because fields accelerate matter. Your fist has mass and velocity. When the wall's electrons push back, they stop your fist in a tiny distance. That deceleration launches a compression wave through flesh and bone. Mechanoreceptors scream, nociceptors fire. Your brain interprets the incoming electrical signals as pain. No atoms interpenetrated. Your momentum simply ended abruptly. Pain is how biology convinces you to keep your macroscopic wave function away from energy spikes. There's a subtlety worth savoring. Touching harder does not bring you notably closer at the atomic level. As you press, the average separation between the facing atoms shrinks only by tiny fractions of a nanometer because the repulsive wall of the potential rises so steeply. Most of the macroscopic compression you see happens in the larger scale cracks and pores between crystals, in the bending of fibers, in the flattening of asperities. At the atomic contact patches, the distance barely budges, the force skyrockets. If never touch feels too absolute, let's define terms crisply. If by touch you mean nuclei occupy the same place, then no, that never happens in ordinary matter. If you mean electron clouds overlap until their combined energy pushes back, that happens constantly and is what we call contact. If you mean our nervous systems report pressure, that is a separate biological layer on top of the physics. The sentence, "You never touch anything," is a way to remind you that what you feel is always mediated by fields, rules, and receptors. This view also explains weird edge cases. Air touches you as pressure. Collisions of molecules transferring momentum via electromagnetic forces. A vacuum doesn't touch you, and your skin's mechanoreceptors relax. Underwater, pressure increases with depth because more fluid above means more collisions and stronger integrated forces. At high altitude, fewer molecules means less pressure, less touch from the air, which is why your ears and lungs notice. Capacitance touchscreens, again, are a perfect metaphor. They don't wait for squish, they watch for field changes. Your finger needn't grind against glass. It only has to come close enough for the grid to register a change. Many proximity sensors do exactly this with light or radio. They infer presence from field perturbations. Nature's version is the lateral line in fish, mechanosensors that register water motion without direct collision. Let's head briefly into relativity, because fields have a speed limit. When you push on a table, does the whole table feel it instantly? No. The electromagnetic forces propagate through the lattice as sound waves at thousands of meters per second, not at the speed of light, because you're moving atoms coupled by bonds, not launching pure electromagnetic waves. The bonds themselves arise from electromagnetic fields, but the information about your push moves as phonons, collective vibrations. Hit one end of a metal rod. A tiny time later, the other end knows. One more favorite confusion. If we never touch, how do we ever cut or break anything? Cutting is controlling where bonds fail. A sharp blade concentrates force on a microscopic area, pushing local bonds over their breaking energy while leaving nearby bonds intact. The cut propagates as a crack where the energy release rate exceeds the material's fracture toughness. None of that requires atoms to pass through other atoms. It requires field-mediated bonds to rearrange or rupture along a path of least resistance. Step out to the edge of fiction for a second. What would true touch look like? If two nuclei actually made contact, the strong nuclear force would dominate. Under the right conditions, you'd get fusion, nuclei merging and releasing energy. That's what stars do, using quantum tunneling to help nuclei overcome their mutual electric repulsion. In a lab, you need extreme temperatures, pressures, or confinement to make such encounters likely. Your kitchen table has no interest in starring in a fusion reactor. It enforces the safe version of no entry, electron cloud repulsion and Pauli exclusion, every day, every second. And finally, the ghostly counterpoint. Neutrinos stream through your body by the trillions every second without touching in any everyday sense. Their weak force interaction probabilities are so tiny that almost all pass through Earth unscattered. That doesn't mean neutrinos are immaterial. It means their coupling to your atoms is vanishingly small. Touch, again, is a word for the coupling was strong enough to make a noticeable transfer. With neutrinos, it isn't. So here's the clean picture to take with you. Touch is not atoms meeting like marbles. It's electric fields and quantum rules resisting overlap. Normal forces are electromagnetic. Friction is bonds forming and breaking, and energy becoming vibration. Adhesion is fields acting at nanometer gaps. Heat is motion you don't track. Your skin is a translator that turns all of that into a vivid sensation we call touch. The sentence, "You never actually touch anything," is not a gotcha. It's a map. It tells you why chairs hold, why hands feel, why geckos climb, why saws cut, why stars don't collapse, and why your phone knows your finger is there before it lands. It's physics reminding you that between every two things is a tiny, powerful gulf, crossed by forces in a dance precise enough to build a world that feels solid. And that, ironically, is exactly why the world is solid. Because, at the deepest level, nothing ever quite meets.